Welcome to this explainer. Today, we're diving straight into some absolutely fascinating new research from Anthropic. We're looking at what happens when you take an AI model entirely out of the chat box and basically hand it the keys to physical hardware. We're going to walk through their recent Project Pilot blog post and really simplify the complex science behind it. Because, this is exactly that pivotal moment where the digital world is finally colliding with the physical one.
So let's dive right into this central question. What actually happens when you let an AI fly a drone? Well, to figure this out, researchers set up an experiment where they handed control of a standard, literally $129 off-the-shelf drone over to a Frontier AI model. Specifically, they were using a DJI Tello EDU. You see, Anthropic's Frontier Red team, working alongside their partners at Andon Labs, they didn't want to test some heavily guarded multi-million-dollar military aircraft. No, they wanted to know if an AI could autonomously pull off a basic locate and follow task using equipment that literally anyone can go and buy online today.
And to understand why this matters so much, we have to recognize that drones are the ultimate dual-use technology. They are tools for both good and bad. So it's absolutely crucial to test how artificial intelligence handles this kind of power. Automated person tracking can be incredibly beneficial, right? Think about search and rescue operations during a massive disaster, or closely monitoring crops in farming. But on the flip side, it opens up these huge, terrifying risks for unaccountable surveillance or even misuse in active warfare. Because AI and drones are both dual use, finding out exactly where their capabilities intersect right now isn't just a fun little science experiment. It's an absolute necessity to ensure our future safety.
The 5-step drone test: how to pass the AI driving exam.
Okay, so to figure out if an AI could actually handle a simple surveillance task, the team at Andon Labs put it through a highly specialized test called Drone Bench. The crucial thing to understand here is that finding a person in an office isn't just one action. It requires the AI to successfully chain together 5 distinct, complicated steps in real time without completely overwhelming itself. First, it has to reconstruct. It needs to map the entire room and spot obstacles. Second, localize. Figure out exactly where the drone is on that new map. Third, navigate. Plan a safe flight path. Fourth, detect. Actually find the target person based on a reference photo. And finally, follow. Keep that target perfectly centered in its view. Now sure, we already have individual human-coded software for these specific tasks, but asking an AI to autonomously grab these off-the-shelf tools, adapt them on the fly, and string them all together flawlessly, that is a massive and incredibly revealing challenge.
The good, the bad, and the crashes, putting the smartest models to the test.
When testing 15 different models, researchers found something kind of hilarious. The smartest AI of the bunch, Claude Fable 5, absolutely aced detecting and following the human, but it struggled so hard with understanding its physical environment. Because it couldn't successfully map the room, it perfectly tracked its target right up until it crashed full speed into a solid wall. The model nailed the detect and follow steps. Actually, scratch that. It performed those steps noticeably better than the baseline human code. But it bottlenecked hard on that very first reconstruct step. It looked at a solid physical wall and confidently decided, yep, that's a doorway. This just beautifully illustrates how AI progress isn't this smooth, magical, upward curve. An AI can be terrifyingly capable in one specific area while remaining completely blind in another. But keep in mind, it only needs that one missing puzzle piece to suddenly achieve flawless, end-to-end performance.
The floor tile trick. AI's MacGyver moment.
Despite all the crashing into walls, the AI demonstrated some incredibly clever problem-solving skills to try and fix its own mistakes before taking flight again. Fable 5 literally analyzed a video feed of the office floor, and it cleverly used the grout lines between the tiles to find the room's vanishing point. Just from that single deduction, it did the math and calculated the drone's camera tilt to within 4 degrees of the true value. No way, right? It even took the initiative to build its own simulated 2D top-down map of what it thought the environment looked like just so it could test and debug its own code before officially flying. It was basically performing local analysis exactly like a human robotics engineer would.
The 6-month gap. Consistency versus flukes.
Let's look at how this builds into a much bigger picture about reliability. Because pulling off a cool MacGyver-style trick once is very different from flying safely every single time. The data reveals a fascinating 6-month gap. Essentially, the frontier of what these models can do consistently today is exactly where their lucky one-off successes were just half a year ago. When researchers ran these flight simulations 10 times, models could hit the human baseline at least once fairly often. It's easy to get lucky once, but to hit that baseline on average, consistently, that takes much longer.
Fable 5's reliable, everyday average performance today is basically a mirror image of the absolute best, luckiest performance from older models 6 months prior. This timeline is a vital metric for us to understand just how fast this technology matures from a viral, one-off demo into a rock-solid, reliable tool.
Keeping humans in control. The cost of automation.
This rapid improvement brings us to a critical crossroad regarding how we manage AI systems that can manipulate the physical world around us. You see, the real danger isn't necessarily a rogue AI straight out of a sci-fi movie. It's much more practical. Once the technology becomes reasonably competent, organizations are going to face immense pressure to remove human supervision just to save time and money. Think about it. In the early days of AI coding, humans double-checked every single line the AI wrote. Now, models execute long, incredibly complex tasks with almost zero intervention. The exact same economic pressure will apply to physical robotics. Right now, keeping a human in the loop is an easy decision because, well, the AI still crashes into walls sometimes. But the very second a drone gets reliable enough to pass the baseline consistently, the overwhelming financial incentive will be to just let it fly totally solo.
So, as we rapidly approach the day when AI can effortlessly pilot robots through our homes, our offices, and our skies, we really have to decide right now if efficiency is worth trading away our ultimate control. Are we prepared to deliberately establish the rules, governance, and robust safety frameworks before AI entirely takes the driver's seat in the physical world? That is the profound, lingering question that Anthropic's research leaves us with. Thank you so much for joining me on this explainer. I highly encourage you to keep thinking about this. Where exactly do we draw the line between helpful, everyday automation and the absolute necessity of human oversight?